This section covers hypothesis testing for population means, where sigma is unknown, and we're going to look at one-tailed examples. As I promised in video 10.2.1, I've included a page like this for each type of test, and this is the test for hypothesis testing for means where sigma is unknown. So if you'll notice, the conditions are the same as they were for testing for means where sigma was known, except of course that sigma must be unknown. The step one is a little bit different because sigma is unknown. Instead of using a normal model, we're going to use a t-model, and our t-model will have n-1 degrees of freedom. For step two, notice the test statistic is now a t-score rather than a z-score. It's the same function, however, except that sigma, which was known in our last video, is now replaced with the standard deviation of our sample, which we denote with S. Everything else is the same. So let's take a look at our first example together. And as we read through it, I'm going to, again, write down the things that are important before we check conditions. So nurses in a large teaching hospital have complained for many years they are overworked and understaffed. The consensus among the nursing staff is that the mean number of patients per nurse each shift is 8. So again, they're telling us that the mean is assumed to be 8. Now that tells us both mu and also our null hypothesis. The hospital administrators claim the mean is lower than 8, so that gives us our alternative hypothesis. To prove their point to the nursing staff, the administrators gather information from an SRS, so that helps us check conditions, of 19 nurses' shifts, so N is 19. The sample mean, X bar, is 7.5 patients per nurse with a standard deviation of 1.1 patients per nurse. So again, not sigma, but S is 1.1. Test the administrator's claim using alpha is 0.025. So that's the summary that I'm going to need on the next page, but let's go ahead and check conditions. We've already addressed that it's a random sample. Obviously, sigma is unknown because they don't give us sigma, but they do give us the sample standard deviation. And n is less than 30 because obviously n is only 19. However, it says assume the number of patients per nurse has a normal distribution. So that is what checks that last box. So again, we have the null and alternative hypotheses that we talked about on the last page. Let's gather our data and do our calculations. For a t-score, remember I'm using x bar minus mu divided by the standard deviation of our sample divided by the square root of n. And again, as I pointed out in the last video, just make sure that you're including the x bar minus mu in a parenthesis and the s divided by square root of n in a parenthesis. Otherwise, a lot of students forget this parenthesis and it makes a big difference. And again, I'll show you how to set this up in Excel with the parentheses so that we make sure that we get the test statistic correct. So our t-score is negative 1.981, and our critical value is now using t inverse instead of norm inverse. So remember, when we do a t inverse, it's okay just to use alpha, and then of course the degrees of freedom. And remember that the degrees of freedom is n minus 1. So in this case, it was 19, which was n minus 1, or 18. So that's where that 18 came from. And then of course, that was alpha. So alpha, comma, degrees of freedom. That gives us our critical value of negative 2.101. So before we find the p-value, let's just remember that if my rejection region is at negative 2.101, and this is obviously a left-tailed test, that means anything to the left or less than negative 2.101 will be rejected, and my t-score is negative 1.981. So my t-score is not in the rejection region, negative 1.981, which will mean that we're going to fail to reject. The p-value is finding, again, and I should have written this on the slide, but this is now a t-dist, and it's, again, t-dist to the left, so it's okay to do t-dist. And then we're going to use negative 1.981, and then the degrees of freedom, which is 18. And we should end up with this value. And again, when we're looking at conclusions, we're going to be looking at this p-value, 0.0315, which is greater than alpha, which was 0.025. And therefore, that tells us to fail to reject as well. So draw our conclusion. Again, both conclusions always should agree, and if they don't, you've done something wrong. Go back and figure it out. But in this case, we're going to fail to reject. Remember, there are three parts to a conclusion. Here's the reason behind our decision. Here's our decision, and here's what it means. So with p less than alpha, we fail to reject the null hypothesis. With 97.5% confidence, or a 2.5% level of significance, there's insufficient evidence, and recall that we're always talking about the alternative hypothesis. So we're saying there's not enough evidence to say this is true, so there's insufficient evidence to support the administrator's claim that the number of patients per nurse is less than 8. Just as we did in our last video, we're also going to take a look at a corresponding confidence interval. So just as we did in our last video, we're just going to use whatever the critical value is that we used for a rejection region, and we're going to use that as the critical value in our interval. So as a reminder, this was x bar plus or minus that critical value, and then this is s divided by the square root of n. And doing all of the calculations, because we failed to reject, that means our hypothesized mean should be inside of the interval, and it is, because 8 is between 6.97 and 8.03. So with 97.5% confidence, we claim that the true number of patients per nurse falls between 6.97 and 8.03. Since the hypothesized value of 8 falls in our interval, this supports failing to reject the null hypothesis. Let's take a look now at how we can have Excel do all of this work for us. Now recall that Excel is just going to do what I tell it to do, and all I need to know as a student is what are the formulas. As long as I know the formulas, for instance, my t-score is x bar minus mu divided by the standard deviation divided by the square root of n. Keeping in mind, I'm going to put parentheses around those. The interval is found by taking x bar plus or minus the critical value, which I'll just call t star, times the standard deviation divided by the square root of n. As long as I know these formulas, that's all I'm asking Excel to do. So let's start with the t-score. The t-score is x bar minus mu. So this is the hypothesized mean, which is mu, the sample mean, which is x bar, the sample standard deviation, which is s, the sample size, which is n, and then of course alpha. And I'm just going to basically plug in this formula. So for a t-score, I'm taking B2 minus B1, x bar minus mu, in parentheses, and then I'm dividing it by, and then parentheses, B3 divided by the square root of B4. So again, don't be intimidated by Excel. We're just using the functions that we know to be true for each type of test or interval. So that's our t-score. Remember that we are then finding a critical value. So looking at our picture, if it's a left side critical value, I need alpha on the left side. So if you'll notice, t dot inverse and then alpha, comma, degrees of freedom. So alpha, and then I don't have a space for degrees of freedom, so I can either create one, or I know that the degrees of freedom is n minus 1, so that's what I chose to do, b4 minus 1. Same thing for the right side. If it's a right-tailed test, I need alpha to be on the right side, and therefore I used the absolute value. Now, why did I choose to do that? Because if I just use alpha, it's going to give me the negative one. And so I can either do T inverse of 1 minus B5, and then B4 minus 1, which is the degrees of freedom, or I can do the absolute value. So whichever one you're more comfortable with, it's going to end up with the same value. Then we need our p-value. So our p-value, again, is going to be a dist function, just as we did with the norm dist. This is a t-dist. Remember, t-dist is going to find the area to the left of our z-score. I'm sorry, our t-score. So t-dist, b7, comma, b4 minus 1, which again is just the degrees of freedom. So if I created a df, I would just point it to that cell instead. And then, of course, comma 1 for true for cumulative. Then to the right, the Excel function actually has a t-dist right, which is nice. So again, I can point it straight to alpha, and then sample size minus 1 for degrees of freedom. Conclusion, again, is just for all of you Excel dorks out there. If p is less than alpha, we're going to reject, otherwise we fail to reject. So that's everything for our test. Now let's talk about our interval. Remember, our interval is found by taking our critical value, and I'm going to use this critical value. Just as we talked about in our last video, the left-hand critical value is going to be negative, the right one's going to be positive. So I want the positive critical value because I want my margin of error to always be positive. And then I'm going to take it times b3 divided by the square root of b4. So this is the margin of error. So again, I'm just plugging that into that formula. And then for my one-tailed interval, I'm going to have x bar in the center, which is b2. And then I'm going to subtract the margin of error, and I'm going to add the margin of error. And we'll talk about all that two-tailed stuff in our next video when we talk about two-tailed tests. So let's go back to the question that we were just working on and enter in our values and just make sure that everything is set up correctly. All right, we have a hypothesized mean of 8, x bar of 7.5, sample standard deviation of 1.1, sample size of 19, and alpha 0.025. So previously we found t to be negative 1.981. That agrees. We found the critical value to be negative 2.101. That agrees. Again, we're doing a left-tailed test, so I'm worried about this column right now. And our p-value is 0.0315. Based on the fact that alpha is 0.025, we're going to fail to reject. And then this is the same interval that we came to together. We're going to look at another one-tailed test, and if you would like, you can certainly skip forward and do this all in Excel, but I'm going to go through this one by hand as well. So a locally owned independent department store has chosen its marketing strategies for many years under the assumption that the mean amount spent by each shopper in the store is 100. So again, that tells us that mu is 100. It also tells us that the null hypothesis is that mu is 100. A newly hired store manager claims the current mean is higher. So again, higher indicates that this is greater than 100. And wants to change the marketing scheme accordingly. A group of 27 shoppers, n equals 27, is chosen at random and found to have spent a sample mean of 104.93 with a standard deviation, S, not sigma, of 9.07. Assume the population of amount spent is approximately normal. Test the store manager's claim at a 0.05 level of significance. Okay, so we have everything we need here. Now let's check conditions. Random sample, it's told to us in the question, random. And sigma is unknown, correct. They've given us S, not sigma. And n, although n is less than 30, it says that the population distribution of amounts spent is approximately normal. So conditions are met, and we have everything we need. Let's move on. So again, we have already written our two hypotheses. The null is that the mean is equal to 100, and the alternative is that the manager believes that people are spending more than 100 on average. Now let's find our test statistic. Again, we're just going to take x bar minus mu, and then divide it by s divided by the square root of n. We find 2.824 for our t-score, and again, that's just the number of standard deviations. Standard errors, our observed value is away from the mean. For the critical value, if I used t inverse 0.05, 26, I would end up with a negative value. And again, this is a right-tailed test. So what that tells us is to the right of this, I need 0.05. And so that's why I'm using either t inverse of 0.95, which I found by taking 1 minus alpha, or you could also use the original t inverse of 0.05, 26, and then just take the absolute value of that because we want the positive value. So whichever way you want to do it is just fine, but you should end up with a positive value of 1.706. Again, that tells me that this value is 1.706, and my observed value is over here somewhere, 2.824. So clearly it's in the rejection region, so we should be rejecting. In addition, we can find our p-value. Again, our p-value going to the right, we're going to use t-dist as we did before, but t-dist actually has a right function. So I can use t-dist right of my t-score, comma, my degrees of freedom. And you should end up with 0.004. And again, 0.004 is less than 0.05. So again, that tells us that we should be rejecting. So draw a conclusion. Looking at first the rejection region, if the critical value is 1.706 and my test statistic is 2.824, that says reject. Also, p 0.004 is less than 0.05, which says reject. So both say to reject. So with p less than alpha, we reject the null hypothesis. So that's the first two parts. Here's the data. Here's our conclusion. And then, of course, what does it mean? With 95% confidence, there is sufficient evidence, because we rejected, we're saying there is evidence to say this is true. So there is evidence to support the manager's claim that the mean spent by each shopper is greater than 100. To create a corresponding confidence interval, remember, don't get caught up in the fact that alpha is 0.05 and therefore we need to create a 95% interval. When we're doing an interval specifically to support a test, we're going to be using our critical value that we found for our rejection region. So again, this is just x bar plus or minus that critical value, and then this is s divided by the square root of n. And we end up with 101.95 to 107.91. And again, an interval should always support what we found when we did a test. So our test, we said, we reject that people are spending $100. We think they're spending more than $100. Based on that, this makes perfect sense. This is saying we think that people are actually spending between $101.95 and $107.91. And therefore, because 100 is obviously less than that interval. It supports rejecting the null hypothesis. Now recall that we have already set up Excel for a left and right-tailed test. So all I'm going to do in this case is simply enter in the values of 100, 104.93, 9.07, 27, and 0.05, and voila, everything is done for me. So again, I encourage you to use the power of Excel to help you with this. And again, we find all of the same things that we had found when we did this by hand, including the values of the interval. So again, I'm looking at the right-tailed test, and I'm looking at the one-tailed interval. Coming up next, we're going to take a look at two-tailed hypothesis testing for population means where sigma is unknown.